Hello everyone. In this video, we'll be studying about relativistic quantum mechanics, which is completely different from the usual non-relativistic quantum mechanics that we usually study. Okay, so this is your relativistic quantum mechanics. If you are if you want to pursue PhD research in high energy physics or particle physics and all that, then relativistic quantum mechanics is very important in that. And so you need to have a basic knowledge so that they will ask a lot of questions from relativity quantum mechanics in interviews if you are appearing interview for position in high energy physics. So yeah, you need to have the basics clear about it. Okay, it's a bit tricky, but we kind of have to do it, and you'll slowly enjoy it. It will take your time. Okay, so like the description of phenomena in high energies actually requires the what investigation of relativistic wave equations. Okay, at relativistic speed almost in the near equal to light. Okay, this means equations which are invariant under Lorentz transformations. Okay, and in non-relativistic quantum mechanics they were not invariant. Here they need to be invariant under Lorentz transformations. Okay, the transition from a non-relativistic to a relativistic description, it implies that several concepts of the non-relativistic theory have to be re-investigated. Okay. In particular, like spatial and temporal coordinates have to be treated equally within the theory. Like, okay, so these things we have to keep in mind. Okay. So before going into detail, I would like to use some notation like in the early on, so that you don't get confused in the latter derivations and all. So the notation, some notations will write. Okay, we know x is equal to x is your written as like the vector r vector like that. Okay, so when I'm writing x, it's kind of r only. So x, y, z, and ict is the fourth coordinate. Okay, four-dimensional space, but all the coordinates have to be same of the same dimension. That's why x, y, z, these are length dimensions, so this should be also length, and this is the complex. So this is called a walled vector. Okay, it's called a same thing, no problem. Okay. Next is a four momentum. Momentum has also four coordinates here. So px, py, pz, and then what I, ey is the four coordinates kind of complex. And this is called a four momentum vector. Four momentum because four coordinates are there. So four momentum. This can also be called a four vector. Okay. Yeah. Then potential, we know magnetic electromagnetic potential is vector potential is A. So it has also four coordinates. So A is equal to what? We can give like vector signs here also, no problem. So A is your AX, AY, AZ, and IA naught. Okay. This is called a what? Four potential. I was doing TFR related videos, but this one is different. And this one like will help you in interviews for high energy physics. Okay. I'll still continue that TFR part, but let's get like you should also have the idea what they will ask in the interviews. If you clear TFR or say Sunlight again. Okay. So next, this is four potential. Next is your V four gradient. Okay, this is called a four gradient. That is sorry. So del by del x, del by del y, del by del z, del by del I del ct. Okay, because see in place of x there should be ict. Okay, so I goes out as a constant, so ct remains inside. C also can go out, no problem. Four gradient. This is the gradient symbol. Okay, so these are some of the notations that we need to be really careful about. So As long as there is no confusion arising, we prefer the this notation. Okay. Okay. There is another one called a metric tensor. You also need to have a prerequisite knowledge of tensor analysis if you are going into this chapter. So a metric tensor is also there. Metric tensor, it's a like you write like this: g mu nu is equal to g00, g01, g02, g03, g10, g20, g30. Okay, g11, g12, g13, g21, g22, g23, g2, so g31, g32, g33. Okay, so this is called a metric tensor. Okay, and its values, like for g00 is 1, g11 is equal to g22 is equal to g32. You will study this in tensor minus 1, and all other quantities are zeros. Okay, so if I write it, only the diagonal components will have some value. G mu nu is equal to 1, minus 1, minus 1, minus 1. All the values are 0. Okay, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Sometimes they also kind of write it like this. Don't get confused if you see it somewhere like this. Okay, so don't get confused. This means all of these quantities are zeros. Okay, yeah. There way one can denote at the length of the vector. Suppose if I denote the length of the vector. Okay. So yeah, one thing you need to know: covariant tensor and contravariant tensor. Covariant tensor and contravariant tensor. Please check it. Contravariant tensor. These two things you need to understand, okay, before going into this chapter. All right. Let me give you a brief idea about it. If you are not sure what is a covariant and what is a contravariant tensor, okay, just a second. I will give you the idea. See, anything you see in the downside, like this one. This is your what? This is a covariant component. Okay, and if you see it upside, this is a contravariant. So that's the difference, and you have to see through this chapter to actually understand it. Okay, you have to go through it, and you have to learn a lot to properly understand it. Okay, yeah. So we'll move next. Now, see, uh, there is this length of the vector can also be written like this: ds2. This is not read as ds square. Okay, ds2 is called dx dot dx, like the product of the. So I can write this one as g mu nu. Okay, sorry, yeah, g mu nu. This is g covariant mu nu, and g mu nu dx mu and dx. Alright, g mu nu dx mu and dx mu nu. Alright. So see, I will give you one thing idea. This dx, see this one, mu is here, so mu is here. Like they can They're cancelling each other. Mu. They're not a cancelling each other. I'm just telling you to understand it for now. Okay, mu is cancelling, mu cancel. So eventually we're getting dx. And g mu nu, we know the value of g mu nu are what, 1 minus 1 minus 1 minus 1. Okay, yeah. Okay. See, this relation is often taken as the defining relation of metricness. Okay, this one. Yeah. So the contravariant form, like this is the covariant. Okay. If I'm writing like this is your covariant form. If they are the notations are like subscript. Okay, covariant form. If I'm writing it upside, that is contravariant. Like with superscript, contravariant. Okay. Alright. So the contravariant form will be what? Let's write. Let me write. So the contravariant form. So the contravariant form will be G mu nu. Okay, of the metric tensor. That will be, if I write it, G mu sigma. See, again I will explain. Don't worry. Sigma nu. Okay, is equal to delta mu nu. Hmm. And it will become 1 0 0 0. Everything will be 1. Okay, here the values change actually. I will tell you. Wait. So see again, this is G mu nu. See, this is upside, so this one is upside, and this was new. So see, sigma, one sigma upside, one sigma downside, so they will cancel out. So nu is left, so nu will go up. You have to understand it like this. Okay. And one thing is, if I am converting this covariant to a contravariant, okay, there will be a minus, like a minus will be there, like g mu nu. There's something like minus g. This is not correct. I'm just trying to make you understand it. Okay, because see, there's one here, but these terms are changing. Okay, minus one, minus one. Are you getting my point? Okay, yeah. Otherwise, I can also write it. Also write it g mu sigma. Okay, g mu sigma is equal to g of g inverse mu sigma, like that. Yeah, this is the perfect way to understand this. Okay, this is the perfect way to understand it. All right. Yeah. All right. There is a thing. Okay, leave it. Okay. Now let's use a contravariant 4 vector. Let's use. We have to give it time. So it's a bit new, and you'll slowly understand it. Let's use contravariant 4 vector. That is contravariant. That means it will be upside, right? X mu is equal to. Don't read it as x to the power mu. Okay, this is x mu is equal to x0, x1, x2, x3. Okay, and you know what is this x3? This x3 is actually this CT or ICT or whatever. Okay, so I will, otherwise, no, sorry, this x here, x0 is actually CT. Okay, we'll take the value CT. X1, x1 is x, x2 is y, x3 is z. Okay, yeah. Um, Here the time lag component is denoted as zero component. So this is called a time lag component. Okay, it has time in it. It's a time lag component. You can write it as the zeroth component of x. Like, so we get the covariant form of the 4 vector by lowering the index. If I lower the indices, I will get the covariant form. This is what? This is contravariant form. This is actually contravariant form. If I lower the indices, I will get the covariant form. See, if I lower the index, it will become what? G mu. So see very carefully, you will slowly understand. X mu is equal to, how will I convert it into what? Covariant. I will multiply G mu nu metric tensor X mu. X what? What should I multiply? Tell me. Because this is mu. Mu is here already. So I have to cancel something out. So X mu. Okay, you have to understand it this way. This is not the process, but you have to understand it this way. They are not actually cancelling each other out. So x mu is equal to g mu nu G mu nu x nu, right? So is equal to CT. Hmm. And now what will happen is see very carefully. See this is 1 minus 1 minus 1 minus 1. These are zeros. So see the x. This is a zero combination. 0 0 G 0 0 G 1 1 G 2 2. This is G 3 3. Okay. So this G 0 0 is 1. That's why this CT is won't change into minus it. G11 because this is okay. Let me explain. Let me expand it. You will very well understand. So this one can be written as what? Again, G00 x0. Okay. Oh, sorry. X0 upward. Okay. Yeah, that will be all right. Then G11 x1 correct. G22 x2 and G33 x3 correct. Yeah, all right. So yeah, now can you do it? Now can you do it? See G00 x0. So G001 x0 is simply CT. G11 is G11 is minus 1 and x1 is x minus x. G22 is minus 1 and x2 is y, so minus y, and this is minus. Did you get it? This is the way to understand this. Okay. Yeah. But if this is yeah. Okay, got it. Yeah. Okay, if I write the exact opposite of this is in what? Covariant form. Okay, if I write like x mu, then what it should be, you can write it now easily. X mu nu, x mu. Got it now? Now getting it slowly. I hope you are getting it slowly. Yeah, it's about own self reflect, like how you can understand it on your own. Even if I tell you 100 times, you won't be able to understand. Okay, so x mu is equal to g mu nu x nu. Okay, just a second. Yeah, g mu nu x nu. So again, what can I write? We x naught, x1, x2, x3. This is a contravariant, right? Okay. This means I want to easily transform the covariant and contravariant, okay, form of a vector and vice versa. Vector means here tensor we will call also vector. Okay, no problem. Yeah. Okay, there is another thing called Einstein summation convention right now. It's easy, easy. Don't worry. Einstein's summation convention. Alright, Einstein summation convention. Like we just add them over the indices and like upper and lower index. Okay, I will show you. So x dot x I can write as x like contravariant mu and x covariant mu. Okay, so I can write it like mu 0 to 3 because we have like 0 to 3 and then x mu x mu. Okay, so I can write it x 0 0 x 0 x 0 x1 x1 x2 x2 and x3 x3. Alright, so we know this as ct and ct. Okay, but this one here, this one is x, this one is x, this is minus x, this is y, this is minus y, z, this is minus z. So this whole thing becomes c square t square minus x square minus y square minus z square. Okay, so this whole thing can be written as like we wrote it first, like this. We know this is actually r vector, isn't it? Xi cap plus in vector normal vector. So we can simply write it as r square, but here we usually write it as x vector. Okay, we just take x vector. We in the beginning we have taken. If you remember, in the beginning I had given you the notation here, x is equal to x vector. So we will just write it x vector, not r vector. X vector we will write it here. Okay, according to notations. So this can be written as x vector square. Got it? So this is your x dot x. All right. Yeah. Oh. So this is the definition of like like okay, wait. Okay, if I write four momentum like that, so we can write like four momentum like P mu is equal to E by zero component E by C P x P y is a small piece, okay, P z. All right, and we write the scalar product in four dimensions, okay, like the one we used in Einstein summation. So P1 into P2, if I write, it will be what, P1 mu P2 mu. Got it? Yeah, like the way we wrote x is x dot x mu like that. P1 mu P2 mu is equal to this one will be what? E. Okay, this one we will write like what? What? P1 0 P2 0 plus P1 1 P2 1 plus P1 2 P2 2 plus P1 3 P3 3. Exactly like this one. If you remember x0 x0, x1 x1, x2 x2, x3 x3. Don't get confused. You can do it easily. Just do it on your own. Okay. This is the mu one. Okay. This is the one we have already taken. Okay. This is the mu part. This is the mu part. Mu part here. Mu. Okay. So again, like x part, this one here, we'll also get something like that. So this is, we know, e by c and e by c. Okay, no change in there, no change in like e1 by c. We can write e1 because this is p1, this p2, e1 e2 plus this one I can write p1, but this one will become what, minus p2, right? Something like that. Or okay, we can write a p1x. Sorry, yeah, p1x, p1x, and this one will be minus, okay, minus p2x x component, and again p1y minus p2y component, I think, and p1z minus p2z. So if I do that, so at the end I will get what, e1 e2 by c square, okay, minus p1 vector p2 vector, because p1 vector p1x is there, p1y is there, p1z, p2 vector p2x is there, p2y, p2z is there, right? So yeah, so this is your what, p1 dot p2, four momentum vector. Okay, yeah, all right. What if we like equally we can just mix the four momentum and the x, like the position one. So x dot p, again x mu p mu, correct? X mu, so it will become like x0 p0 plus x1 p1 plus x2 p2, okay, plus x3 p3. Exactly, we can derive in the same way. Okay, and what will I get? Because x0 is what, ct, p0 is what, e by c. Again, x1 is x, p1 is px. Okay, but this one is covariant, so I can write it here as minus px. Okay, x2 is y, p2 is minus py, because this is, if it was p2 like that, it would have been py only, but this is covariant, so minus py. So again z, and this is minus pz. Okay, so cc got cancelled, et minus xpx minus ypy minus zpz. Okay, this one will make it clearer. Et minus, we can write this as kind of x vector dot p vector. Is that correct? Because if you remember, if suppose it was in vector, simple vector form, simple suppose, so could I have written like this, xi cap plus yj cap plus zk cap dot pxi cap plus Py j cap plus Pz k cap. Okay, and simply multiply them. I would have got this exactly like that. So this is your R vector. This is your P vector. So here in place of R, I'm writing X. That's it. Simple. Okay. Yeah. So this is the expression for what? X dot P. Okay. Einstein summation of X dot P. Yeah. Pt minus this. All right. I hope I understood till this point. Yeah. Okay. Now, uh, okay. So let's do something. For momentum operator, okay. We'll expand it a bit. We'll see what's going on here. So momentum operator we know is what? Minus IH cut del by del x, right? Minus IH cut del by del x, px, py. It goes on like that, right? So suppose I write p mu. So it will be what? IH cut del by del x, okay? Del by del x mu, right? Yeah. So it will give me what? It will give me IH cut del by zero component is CT, IH cut del by del, this is x1, sorry, IH cut del by del x2 square del by yes. Yeah, all right. Yeah, so this I can write, this I can write it IH cut del mu like this. Okay, I have to write like this. So this one will become IH cut, sorry, yeah. Mm, okay, we can do one thing. Okay, yeah, IH cut del by del CT minus IH cut, it will be minus IH cut del by del x. Till now, I think you have understood, so I won't explain again what is why it is minus, why it is plus del by del z. Okay, so I will take the IH cut out. We have done it so many times now. The minus, this one plus is minus. Okay, no problem. Minus del by del x. Yeah, I can write this thing as what? Del. Right. So IH cut minus. Is that all right? Okay, is that all right? I hope I understood. Yeah, yeah. Just write it down. Just absorb it a bit. Then we'll go move forward. If you like this video and if you need tensor analysis, then only I will do. Let me know in the comment section if you need. Only if you tell me, otherwise I won't do. I see no comments, nothing else. I don't even know whether anyone is watching my videos or not. So if you only comment, then only I will know that someone is watching my video. Otherwise, it will be just pointless. Okay. Okay, let's move one more step ahead. Suppose if I write transforms like a contravariant with suppose p mu. So how will I write it? I h squared I h so minus h squared square del by del x. This one is contrast, so this one will be co, and this one will be okay. This one is okay. So minus h squared square 1 by c square del square by del t square. It's a double derivative now. Okay, minus of simply again, if you see, it will be del square del s square. Okay, del square del square del z square. So I can write it like minus h squared square 1 by c square del square del t square. Okay, minus what do I say? Del. Okay, it can be written as del. This whole thing. Okay. So this whole thing is written as minus h squared square del. This is a nabla operator, and this is what exactly this one is. This one is actually del. This one is actually 1 by c square. Okay, this is called D'Alembert operator. You must have studied in like classical dynamics. Alembert operator. Okay, all right. Yeah. Is it all right? Okay. Now we'll do what? Let's check the commutation relations of momentum and position. So I only check it simply p mu x mu, yeah, x nu suppose. We cannot give them the same. Suppose p mu x nu. Okay, so it will be ih cut. What is p mu del a del by del x mu? This is contra. This is x nu. X nu is what? How can I write g nu delta x delta? Yeah, that's it. Sorry, nu sigma x sigma. Yeah. So ih cut. If I take the derivative and all, del x mu, and this is actually constant, so it doesn't matter. Minus g mu nu x. So this term will be kind of vanishing. So only this term will remain. So ih cut um, g nu sigma del x sigma by del x mu. Okay, del sigma by del x mu. Okay, so this has another rotation in tensor analysis. So again, if you want tensor analysis, then only I will do. Otherwise, I'm not gonna do. If you tell me in the comments, then only I will do. This has a delta mu. Okay, see, it's a kind of a, you don't get confused again. Okay, So I can write it I h cut g nu delta, sorry, sigma delta sigma mu is equal to delta cancel out g nu mu. Okay. Yeah. Yeah. All right. So yeah. So this one I can write sigma sigma cancel out I h cut g mu nu. Okay. This is kind of the one if you multiply with. So, yeah. Actually, it is g nu mu, which is equal to I h cut g mu nu. Okay, no problem with that. All right. Yeah. So this is the one. If you see p mu x nu is equal to I h cut g mu, right? So let's check the things we have studied so far in quantum mechanics. Let me write again p mu, sorry, x nu commutation relation is equal to I h cut g mu. So if this is px, suppose in commutation px x, so what it should be I h cut g x, x is of which component? 1. X is not 0, x 1. So g11, g11 is what? Minus I h, because x px would have made what? I h. Alright, is it alright? Yeah. Okay. Hmm. So this is the thing. Okay. So exactly like this, we can also get the four momentum, four potential of electromagnetic field. That's four potential electromagnetic field. Okay, and A mu is equal to A zero A vector. So I can written as A zero. A we know A one A x A y A z. Okay, and this can be written as G mu nu A what nu, because nu will be cancelled, we will get A. Okay, so A mu r what here? A mu r contravariant, because this mu is contravariant, it's an outside, and A mu is covariant. Okay, yeah. So from A mu, the electromagnetic field tensor can be written. Okay, from A mu we can write electromagnetic field tensor, which is F, written as electromagnetic field tensor. Okay, so you would have studied it in relativistic electrodynamics. We'll do that also, no problem. F mu nu is equal to del C, when it is written like that, del A mu del A nu. Okay, del A mu del A, sorry, it should be minus del A nu del A mu, like that, just like that. Okay, so this one we will do. Okay, in the next class we will derive it, derive the matrix, complete matrix in the next class, in the upcoming class. Okay, when I will realize that, like when I would have taught you enough like these things so that you would have some idea. Okay? Then only I will do that. Okay. Okay. So these are the prerequisites that we need for relativistic quantum mechanics. Okay. We won't do too much. That will be heavy. So this is enough for today, and practice it again and again. I will urge you to practice again and again so that you can understand it. Okay. Yeah. I will give you some references to read from some books you can follow. Like, don't go too many follows, don't follow. Broken Drill. I'm sorry, I have actually forgotten. Yeah, J is yeah. Okay. And now is Grinder. You can follow that for easier explanation. Yeah. So these two books you can Broken Drill and Grinder. Okay. And you can follow another UC Day for tensor analysis. If you tell me in the comments, then I will do the video on tensor analysis. Okay. Okay then. That'll be it for this class. We will study more in the upcoming sessions. Thank you very much.